Welcome to Lecture 7, Inverse Trigonometric Functions. Let's begin by reviewing something that you should already know. Suppose we have a function, f of x, whose domain is D, domain is the input, and whose range, that's the output, is R. Then f inverse of x is the inverse function of f of x if it has, so first of all, it has to have domain R and range D. These two things are flipped. So this has to hold, but also f inverse of y equals x if and only if f of x equals y. So basically the inverse function, as you know, it just reverses the role of the input and the output. And that's it. So a few easy results. The inverse function of the inverse function is the function itself. And also, if you apply the function and then the inverse, you get back x, what you started with. Or, if you first apply the inverse function and then f, you get back what you started with. It's just now it's y, because it's in the range. So a picture of this, if this is x, and you apply f, and you get y, this is f of x, then to go backwards, you need to apply f inverse. F inverse is a function that takes you from y to x. So this is f inverse of y. Okay, so a few comments. For a function, so for a function to have an inverse, it must be one-to-one. It must be one-to-one. And one-to-one, remember, means that if f of a equals f of b, then a equals b. One way to think about what this condition means, so I'll give you a couple ways. One way, just sort of abstractly, is if you have a that maps, if a and b both map to the same element, let's say c. So this is f of a and f of b. So both of these are f equals c. Well, that can't happen. So if it secretly does, then that means that a and b are the same to begin with. So like if f of 1/2 equals f of 2/4, we know that 1/2 and 2/4 have to be the same. So another way to think about what one-to-one means is that it passes the horizontal line test. So an example of here's an example of a one-to-one function, because no matter how you draw a horizontal line, it intersects the graph only once. A non-example is something like this, because here where you draw a horizontal line, it intersects the graph multiple places. So there are multiple there's multiple points A and B that equal the same output. So another comment is the function f inverse of x is the graph of this, but f inverse of x is the function, I'm going to say reflected across the line y equals x. And so, well, I'm running out of room here, but I think I can fit it in here. For example, suppose here is the line y equals x, and again, this shouldn't be new. You should know this. But suppose if this is your function f of x, then your inverse function is what you get when you reflect. This is f inverse of, I should say this is f inverse of y, I should say that. So these two functions are the same but reflected, or are mirror images across this line, y equals x. So a familiar example of this that we have seen recently is that the natural log function is the inverse of the exponential function. So this is, I forgot I was still on blue, but that's okay. So if this is the line y equals x, so the natural log function looks like this, and the exponential function, so this is intersects at 1, so this is the natural log of x, and then the exponential function looks like this, and this intersects at 1 as well. And these, of course, are this is a horizontal asymptote, and this is a vertical asymptote. So just to check, so to check with this thing is, let's check the domain of e to the x. So the domain, or the input of our, well, let's label our function. So let me call this, well, I guess I called this f of x, so I have to call this f inverse of x equals e to the x. So the domain of e to the x is, the input is everything. So that's going to be it's going to be negative infinity to positive infinity, and the range of the natural log of x, notice the output of the natural log, that can be anything this direction, so that's the same thing as it should be. Next, let's check that the range, so we started with the domain of e to the x, let's check the range. So the range of e to the x, that's the output. So the output is well, non-negative numbers. So that is 0 to infinity, and the domain of, not e to the x, of natural log of x is, that's the input of natural, that's going to be all non-negative numbers, so that's going to be the same thing. And so notice these are the same. Let's try that again. These are the same, and those are the same as they should be. Okay. The topic of this chapter is inverse trigonometric functions, so let's start with our most basic one, y equals sine of x. So first of all, does sine of x have an inverse function? Now you have to be careful here, because let me draw sine of x. So this is, so this function is not one-to-one. Notice it easily fails the horizontal line test. That's on the domain of the function. So let's write that down. This is, so how do I want to say it? So let's see. Does sine of x have an inverse? That's this question. Oh, and let me call this f of x, just to be clear. And so So there's one problem, as I pointed out. One problem is that sine of negative pi equals sine of pi equals 0. So this is not 1 to 1. Now there's more than just pi, negative pi, where this is not 1 to 1. But one solution is we can restrict this function. This is f of x equals sine of x. We can restrict the to the domain negative pi over 2 to pi over 2. And we don't need to pick this domain, but this is typically the domain that is chosen. So right here, this is negative pi over 2, and this is positive pi over 2. So this is the interval that we are choosing, and you can see that our function is clearly 1 to 1 on here. Okay, so the inverse function of sine of x on this restricted domain is just this thing reflected across the line y equals x. So let's be careful when drawing the line y equals x, because this is not necessarily to perfect scale. So this is pi over 2. Let's see, so this up here, that's 1, and this is negative 1. And so pi over 2 is equal to, well, roughly, so half of 3.14, so it's definitely more than 1. So the line y equals x is going to go more like something like this. So if you reflect, see if I can do this without messing it up. It's harder than it looks at first. So if you reflect this function, you get something that looks like, let me do a piece at a time. So here I'm reflecting this, so now I'm reflecting this piece across this line. And now let me reflect this piece across this line. And if I do that, I get something like that. So this here is going to be the line. This is f inverse of x equals inverse sine of x. Or sometimes this is called arcsine. So to summarize, y equals inverse sine of x, or arcsine of x. This thing has domain. Let's be careful. Has domain. Well, the domain of this is the range of this blue function, which is from negative 1 to positive 1. So the domain has to be negative 1 to positive 1, and it has range negative pi over 2, pi over 2. Maybe I haven't drawn this perfectly. This thing, what it's supposed to look like, a little more accurate, is supposed to be more like that. Sort of like a cubic, but it's not a cubic. Okay, so to label these axes again, this here is pi over 2. This down here would be negative pi over 2. And this point here would be 1, and this point here would be negative 1. And that negative 1 is where this lines up. Okay, so as an example for this, so let's just do a quick example, just so we can get used to this. So inverse sine of 1/2. So let's figure out what this is. So to do this, well, what is this? Let's ask ourselves, well, here's how we should figure this out. So sine, regular sine of what function equals 1/2? Now, sine that is on this interval. So that's, now because this function is 1-to-1, there's only going to be one answer, one thing where sine of that is equal to 1/2. And so that's going to be pi over 6. And so inverse sine of 1/2 is pi over 6, and that's because sine of pi over 6 is 1/2. And, I should say, and pi over 6 is in our restricted domain, pi over 2, negative pi over 2 to positive pi over 2. Okay, let's see if there's anything else I wanted to say about this. Well, just as a summary, I guess. Sine inverse, or inverse sine of x equals y, if and only if sine of y equals x for negative pi over 2, where y is between negative pi over 2 and positive pi over 2. And that's, again, the domain and the range we saw are reversed, and these are inverse functions because this holds here. Okay. Similarly, we can define arc cosine of x on a restricted domain. This one, if I remember, is a little harder to define. A little bit harder to draw. So let me try here. So cosine looks like, and it goes like this. So now in principle we could pick any interval where this is 1-to-1. So notice we cannot pick negative pi over 2 to pi over 2 like we did before. It's not 1-to-1. We could pick this interval, but we're going to pick this interval because it's probably the most natural. And this here, it looks like it goes across or even up, but it's supposed to go steadily down. So this is pi. That's pi, not pi over 2, because it's half of a full cycle. And this here is 1. So this here is pi over 2, so that's going to be about 1.5 roughly. So the inverse function intersects 1. And let's see if I can draw this. It's going to be something like that, where this is the line y, it's supposed to be the line y equals x. I guess I should say that our function, our cosine function on the restricted domain is going to be on this blue domain right here. And then the inverse function is going to be on this piece, where this is going to be pi over 2 on the y-axis, and this is 1 down here. And I'm sorry, this is not pi over 2. That's just pi, and this is going to be pi over 2 up there. Okay, so let's summarize. Let me switch colors. So for f of x equals cosine of x, we restrict the domain to 0 to pi. So let me draw that this is f of x equals cosine of x, and this is f inverse of x equals arc cosine of x. Okay, so again, these are inverse functions because the inverse cosine of x, also known as arc cosine, of x equals y if and only if cosine of y equals x. And this, of course, is for only values of y in the domain. Next, let's review the arctangent. So remember, tangent, unlike the others, so let me write this down first. F of x is tangent of x equals sine of x over cosine of x. This is not defined anywhere where cosine of x is equals 0. So this is actually not defined at all, not defined at x equals plus or minus pi over 2. Now, there's, and then every integer multiple of pi, more or less than that, but right now I'm not concerned about that. We're just going to look at the, if this is pi over 2, I guess negative pi over 2, and this is positive pi over 2, then tangent looks like this function. It goes through the origin, and then these are both horizontal and vertical asymptotes. And if you remember, right, that this thing repeats like this, so this is not a continuous function. Okay, so it's natural to just take the fundamental domain of tangent to be, well, this. So this function is 1 to 1. So it's going to have an inverse function, and that inverse function, let me try to draw this. Let me first draw the line y equals x. So that inverse function is going to look, it's going to look like that, and then it's going to look like, oh, let's do that better. It's going to look like it's going to intersect there. It's going to look like that. So notice, just like how this guy has a vertical asymptote, this thing has to have a horizontal asymptote. Maybe I should have drawn that a little more accurate. So this has to have a horizontal asymptote. And let's see, do I want to add? Yeah, let's add. That asymptote is going to be at pi over 2, and this asymptote down here is going to be, let's extend this, it's going to be at negative pi over 2. And that's complementary to these vertical asymptotes of plus or minus pi over 2. Okay, so here we restrict domain to, now we got to be careful here, it's negative pi over 2, positive pi over 2, but here we are, notice we have the open intervals. We're not including the endpoints because it's not defined at the endpoints. So now let me switch to a pen. So now the inverse function is f inverse of x. I should probably label this. This is f of x equals tangent of x. And then up here, this is f inverse of x equals arctangent of x. And you're free to use arctan or inverse tangent of x interchangeably. They mean the same thing. So inverse, well, my experience was, where I went to high school, we always learned inverse tangent. That's what I saw in the books. That's what my teacher used. And then when I went to college and I looked at other books and looked online, I noticed that arctangent seemed to be prevalent. So I got the sense that I learned inverse tangent, but everyone else learned arctangent. So when I got to college, I saw them used interchangeably. So I don't know if it's a regional thing or if it's just a time, like a certain decade, one gets more popular, or based on what book you use, but I use both of them interchangeably, and you should too. So the inverse, back to here, this is inverse tangent of x, or arctangent of x. And now, what else do I want to write down? Well, let's just note the asymptotes. So the limit as x goes to pi over 2 from the left, so the limit, this vertical asymptote is of tangent of x equals infinity. And similarly, where do I want to write this? The limit as x goes to pi over 2, I should say negative pi over 2 on the positive side as we go in this direction, then that limit is equal to negative infinity. So these things, here are vertical asymptotes, and I'm just going to leave it abbreviated because I'm not 100% sure I can actually spell asymptotes. Now, for the inverse tangent, notice that the limit, so the sort of the dual of this one is that the limit as x goes to infinity of inverse tangent of x equals pi over 2, and the limit as x goes to negative infinity of inverse tangent of x equals negative pi over 2. So this is the x value and the y value, x value and y value. These are reversed in the for the inverse function. So these are horizontal asymptotes. I guess that should probably be a p. Yeah, over there I said p. I should make that a p. So again, do I memorize all these things word for word? No, I just draw the picture, I look at it, and I understand it. Okay. Okay, let's do the other three inverse trig functions. The first three that we've seen are the ones that I want you to learn and memorize. The other three, they come up, but I'm not gonna. I think they're a little more obscure: cotangent, secant, and cosecant. But so let's first do cotangent. Now remember, cotangent of x equals 1 over tangent of x. So y equals the inverse cotangent of x. This is the value of y as such that x equals cotangent of y, where y goes from 0 to pi, non-inclusive. So the domain of let's say the domain of this is going to be negative infinity to positive infinity. Next, secant of x is 1 over cosine of x. So y equals inverse secant of x is the value of y such that, so that's supposed to be a such that x equals secant of y, where y is from 0 to pi. And now, be careful here, y cannot be equal to pi over 2, because when y is pi over 2, it's not going to be defined. So the domain of this guy, let me, how do I want to arrange this? Yeah, let me circle this. So the domain of this one is absolute value of x is greater than or equal to 1, which is the same thing, equivalent to saying either x is less than or equal to -1 or x is greater than equal to 1. So this is on the number line, this is going to look like 0, -1, 1. Well, that's not balanced, but it's not great, but it's going to look like all these numbers. And that's because what we're doing is 1 over cosine of x. This is 1 divided by some number that is at most 1. So we're always going to get a number that is at least 1 in absolute value. Okay, so finally the last one. Remember, let me switch to black. Remember, cosecant of x equals 1 over sine of x. Now this is going to be a number, again, that is either at least 1 or less than or equal to -1. So y equals inverse cosecant of x. This is the value of y such that x equals cosecant of x, where y is now between -pi/2, pi/2, and now y cannot be equal to 0 because that's what's going to make, because that would mean we would divide by 0. So once again, the domain for this is going to be the same as the previous one. So what I want you to do is don't worry about these three. They're there, but they don't come up that much. What I want you to do is focus on remembering inverse sine, inverse cosine, and inverse tangent. So next, we're going to look at the derivatives of the inverse trig functions. None of these are things you should be able to do in your head or see why they're true. You can look at the derivations in the book, or Google them if you want to. They're worth looking at, but I don't think they're worth deriving in a lecture. So I'm just going to give them to you. I want you to memorize the first three. And the last three you don't have to have memorized. They don't come up nearly as much. But you should be able to use them if I give them to you. So the derivative of inverse sine is 1 over the square root of 1 minus x squared. And then the domain of this, so you don't have to memorize. If you've memorized this, then just the function, then you can look and say, when is this thing defined? So this bottom is defined as long as x squared, well, this square root has to be, it can't be 0, it would be dividing by 0, so it has to be strictly greater than 0, so this x has to be strictly less than 1 in absolute value. So this is going to hold for x between 0 or -1 and 1. So our cosine of x has a similar derivative. It's actually negative times that. So it's negative root 1 or over root 1 minus x squared, and it's going to have the same domain as well. So this is not something that really should be expected, that you get these inverse cosine functions and their derivatives happen to be these functions with square roots in them. So the a derivative of arctangent is 1 over 1 plus x squared. And now we look at this and say, well, that's defined for all values of x, all real values. So I'm going to say this is for x, all x between negative infinity and infinity. And then in our cosine is the same thing. It's just the negative of this. And so that's one I guess you can memorize just because it's kind of quirky that they're off by a negative sign. So let me put braces there. So this domain is for both of these. Then the derivative of arcsecant is 1 over absolute value of x times square root of x squared minus 1. Notice this is not necessarily going to be differentiable everywhere. I would suspect that at x equals 0 there's going to be some corner issue happening here. And finally, the last derivative, or the last inverse trig function, derivative of cosecant of x is going to be negative 1. So it's the negative of this, so times square root, or absolute value of x times root x squared minus 1. And both of these are only valid for absolute value of x greater than 1. Because now you need this under the square root sign. That has to be positive, so that means that x has to be at least 1 in norm. Okay. Let's finish with an example of an integral that we have previously not been able to do. Okay, so consider the integral. Let's integrate from negative 3 to 1 of dx over x squared plus 6x plus 13. Okay, so let's write that out better. So what I want to do, and the first time you see this, it may seem a little bit weird out of left field, but I'll try to oh, I need to make this negative 1, so negative 1. I guess it doesn't really matter, but just to follow the example that I have in the notes. Okay, so what I want to do is I want to write this as dx. Well, I look at this, and the inverse trig identity that this reminds me the most of is that the derivative of arctangent of x equals 1 over x squared plus 1. So I look at this and I'm like, well, that looks a little bit like this. Perhaps I can complete the square and do some sort of u substitution. So, okay, so how do I want to write this? Well, let's write this as x. I would like to have x squared plus 1, but I don't. So I have x plus something squared plus something right there, right? So, okay, what goes here? Now so this 6x has to be twice this term times that term. So this has to be a 3. And now if you multiply this out, we have x squared plus 6x plus 9. So this term here, that's a 13. So this has to be a 4. Okay, so from here, now we're looking, this looks a lot like this, or maybe a little bit like this, depending on your perspective or your optimism. But now let's do a u substitution, and I'm going to let that be equal to u. Okay, so if we do that, let's let u be equal to x plus 3, in which case du equals dx. Okay, so now our integral becomes, let's see, so we have u squared plus 4. On the top we have du. Ooh, now we've got to be careful to see what our limits are. So let's do that here, and let's be careful. So so the upper limit, u equals -1 plus 3. So I'm plugging in x is -1. That is equal to 2. And our lower limit, u equals -3 plus 3. So this is -3 plus 3. That equals 0. So this integral actually goes from 0 to 2. Okay, so now we don't quite have what we need. Again, we have, this is what we need, this is what we have. So how do we fix this? Well, I have to factor out a 4 here because this thing has to be a 1. So one way to do this is I'm going to look at this and I'm going to say, well, so I'm going to integrate it from 0 to 2. Now I got to put a 1/4 here, du. Now I got to put a plus 1, and then I have to figure out what the heck goes right there. So there's, let's see. So let's put a this is a u squared divided by 4. All right? Have I done that right? You can do anything you want if it's true, and that looks to be a true statement. Okay, great. So let's simplify this. This is the integral from 0 to 2 of, well, I guess I can pull the 1/4 out if I want to. Yeah, let's do that. Let's put the 1/4 out there. And now I have at my bottom, I have u over 2 quantity squared plus 1, and I have du on the top. So now I do another, well, now I'm a lot closer to what I want right here. So I can actually do another u substitution. Let me switch to blue now. So now I want this thing to be my new u, so I'm going to call that a v. So let v be u over 2. So dv equals, what is it? So dv equals 1/2 du. And so now I want to solve. I want to plug in for du. So that's going to mean that du equals 2 dv. And that is what I want to plug in for that. So now my integral becomes, let's see, 1/4. Integrate, let's do the bounds later. 1/4 integral from, well, let's see, 2 dv over v squared plus 1. And now, well, let's check these bounds. I'm going to do those up here. So the upper bound is when u equals 2, which means that v equals, let's see, 2 over 2 equals 1. And this lower bound is when v equals, or u equals 0, so u equals 0 over 2 equals 0. So this integral is from 0 to 1. And now we know how to integrate this. I'm going to pull out the 2. So if we pull out the 2, what we have right here matches exactly what we have right there. So notice this thing here, it just tells us in reverse the integral of 1 over x squared plus 1. I should put a dx here. That integral is equal to arctangent of x plus c. And that's exactly the useful piece of information. So I'm going to write this now as, let's pull out the 2, I get 1/2 from 0 to 1 dv over v squared plus 1. So this is going to be 1/2 of arctangent of v, I evaluated from 0 to 1. So let's move over here to make sure I have enough room. So that's 1/2 of arctangent of 1 minus arctangent of 0. So we got to be careful what this is. Now what I do is I still to this day like drawing the unit circle. And where is arctangent equal, or where is the tangent equal to 1? That's equal to 1 right there at pi over 4. And where is the tangent equal to 0? That's equal to, the tangent is equal to 0 right there. So this here is 1/2 times pi over 4, that's arctangent of 1 right there, minus 0, which is pi over 8. And that is our final answer. And this is a neat little problem, because until we learned about inverse trig functions, who knew that would be useful in solving this? Until we knew about that, we didn't really have any way to evaluate an integral like this at all.